The problem states, given two doubly linked lists of any size, insert nodes of the second linked list into the first list at alternating positions of the first list without making any copies of the nodes. In this problem, the interviewer is first getting your understanding of doubly linked lists. Second, they are getting your understanding of how data is allocated on the data heap. Specifically, they're trying to suss that knowledge out by saying alternating positions of the first list, and the crucial part is without making any copies of the nodes. The third part is they want to test your attention to detail. In the problem, note here that the first list and second list are both of length 5. Somebody without much attention to detail might get focused on this particular case and miss an important part of the problem where it says given two doubly linked lists of any size. So we have to account for if the first list is smaller, if the second list is smaller, and if either of the linked lists are empty. So here what we're going to do is first in main, what we're going to see is we are going to have 3 doubly linked lists. I have a doubly linked list 1 and a doubly linked list 2. In a typical code segment for this problem, these 2 lines of code are sufficient. I'm adding another DL list called empty because I want to test to make sure that when I have freed my memory and properly allocated the doubly linked lists, that I do not encounter any segmentation faults. In this particular case, I have added 5, 7, 17, 13, and 11, and here I have a list with a different length. I'm going to show you the merge lists method in a little bit, but crucially, note that I add 2 more to the second doubly linked list and run it again. This is to see if I am properly allocating the pointers and don't run into any segmentation faults. So what we're going to do is we're going to pass an argument as one of the linked lists to the other. So in this case, I'm going to say we're going to pass the second list to the first list as a method. Then we're going to put the nodes in alternating order without making any copies. So if we had 10, 14, and 13, we have 7 and 12. What we want to do is 10 is originally pointing to 14, but we're going to update it so its next pointer is pointing to 7. And then 7's next pointer is going to point to 14, 14's previous is going to point to 7, and then 14 next is going to point to 12, like so. So that is a correct solution. What we cannot do is we can't say, all right, I'm going to create another 10, I'm going to create another 7, I'm going to make a new node, and we're going to ignore everything. That's an incorrect answer. So let's think of some potential problems that we might have while trying to solve this issue. One, because the problem states a linked list of any size, we don't know the length of either linked list. A potential solution is to keep account of the number of elements traversed in each list. However, your interviewer might say that that's not allowed, and they likely won't allow you to do that. So let's address another risk. We can't make a copy, meaning we cannot just insert values into another linked list. So what we're going to do is we're going to call the second linked list with a call by reference to the first as a method. The next thing is that the list of nodes is a private member of the class. We've designed this specifically to do aggregation and encapsulation so that when we call the delete method and free all the memory off the data heap, we don't have unintentional double freeze and we don't produce that memory map error. So what we're going to do is we are going to call the second doubly linked list by reference. So that way when we're done with the second list, we can prove that it's empty and it's been changed in the method, and we can preserve all of the changes. So how do we do this? Here are 2 doubly linked lists, and it's actually the example that I have coded up. So what we can do is first we're going to move the nodes. What we need to do here is that the head pointer, see if I can do it, there we go. So the head pointer of the second list is pointing here. At the solution, the second list should be empty. So what we're going to see is that the second doubly linked list is going to eventually have its head and tail not pointing to anything. So at first, what we're going to do is we're going to use our walking method. are going to use cur and next, and we're going to update previous and next, so that way we know that we can connect these four. What's going to happen is the solution should say that next for 5, instead of pointing to 7, should point to 12. 12's previous, instead of pointing to null, should point to 5. 7's previous, instead of pointing to 5, should point to 12. And 12's next should point to 7. We see in the animation, we're going to update this. So here's how we start in the code. So I'm calling this part 1 and part 2. You should go to lines 310. So this is what you will see. And so I'm going to go to the solution code, which is over here, I believe. Here we are. Let's scroll. There we go. So here is what you're going to write. First, I'm going to say if it's this list is empty or the merge list is empty, we're going to say the list is empty, no merge. Now, we do not need this arrow to access the private members. However, I've included it just as a reminder of how to do pointers and how to differentiate between the two lists. Likewise, at line 318, I could do this head and it will compile and run just fine. The next thing we're going to do is we're going to set up these first and cur pointers. Now we have first and second. Cur is pointing to, first cur is pointing to the list head that we want for the first list for the solution, and second cur is pointing to the merge list. And we've set up first next and second next to be updated. Then what I do is I set the merge list head pointer to null because the merge list should be empty when we're done. So now what we need to do is we need to keep track of the nodes or the list will break. So what's going to happen is we're going to update the previous nodes. So we're going to see that 7's previous now points at 12 and 12's previous now points at 5. Then we're going to update the next node. So we're going to see that 5's next points to 12 and 12's next points to 7, like so. So now how do we move cur and cur next without 5 and 12? We want this node to move over here and this node to move over here. However, what you may notice is that 5's next is pointing here. So all we need to do instead is just saying, well, we're going to move this one to point here, and we're going to move this one to point here. And we already have pointers pointing to that same location. So we're just going to update it like so. First cur equals first next, and second cur equals second next. And now we're in a scenario where we have the next pointer where we want to go here. And that's what we're going to do. We're going to move that over, and now we're set up, and we're going to continue to make this kind of move. So now we've added some updates here. Now this is not what you're going to code, because I'm going to make some modifications because this actually doesn't quite work. But this shows what I've just done. We've updated and we've moved to the next code. So what does work and why doesn't this work? Well, we have a scenario that we have to figure out when it is we're going to stop. And remember, they can be lists of any length. So we could have a scenario where we have one node in the first list and 20 in the second list, or 20 in the first and 1 in the second. We have to account for those and avoid segmentation faults. So we're going to continue here with a wrong answer. This wrong answer is we're going to stop when first or second next is equal to null. And so these are our next nodes. And so that would be if we're pointing at null. But let's see what happens when we actually do this. So I'm going to update the previous and next nodes here. I move. I update the previous and next nodes here. I move. And then we encounter our problem. I have said second next is equal to null and we're terminated. However, we don't have the proper link between these two nodes. So what are we going to do? Let's consider another wrong answer when first or second is equal to null. So as currently constructed, the first or second will go to next, then null next actually doesn't exist. So we produce a segmentation fault. So what do? Let's do a combination. Let's set node next equals node first next while inside the while loop. This will allow us to hit the correct termination state and avoid the segmentation fault. And so now this is going to be closer to what it is you're going to actually code. So let me show you here. While first is not null and second is not null, we're going to update like we've done. And then here's the change that I'm going to tell you to do. First next does not equal null. Then we're going to perform the update. Otherwise, we don't need to perform that because that will produce a segmentation fault. And then in all cases, we want to update the cur to point to the next. This is a solution that will avoid the segmentation faults in all possible cases. I will discuss these last little lines in a moment. So does this work if the full list is shorter? We update everything. And so in order to avoid that, that is the code that we need to do here with this if statement. To protect the shorter first list with the if statement, if the first list is shorter, then we set the tail equal to the second, which is going to be this last bit of code here. If first cur does not equal tail, so we've reached the end of the while loop, we are going to set the tail of the linked list that we want our solution to point to the merge list because the second list was longer in this case. And then we are going to set the merge tail equal to null, which means that head pointer for merge list is now null and tail is now null, and we've avoided all potential segmentation faults. So that's the last part that I have here to make that change. And so to show that it actually works, I am now going to run it. And this is what's going to run when you update your code. And now we have all of these cases here. We have 5, 7, 17, 13, and 4. We see that all the lists end up here. Then I pass that full list and an empty, so we don't do any merge. I reverse them, and we see that it ends up correctly. And then in list 1, what I do is I put 30 and 27. I put that full list, and we see that it goes 35, 27, 12, and so on. And this is the correct solution.